A rod of mass m and length d is attached to a frictionless horizontal surface by a frictionless pivot at the left end. The rod is initially at rest, and a disk of mass m over 3 moving toward the rod with velocity VO perpendicular to the rod. It hits the rod a distance x from the pivot point. So in part A, when the disk hits the rod, suppose that only one of three situations may happen. It can either stick to the rod, it can come to rest, or it can bounce backward. We want to rank those situations according to the resulting angular speed of the rod. So this is much like just regular conservation of linear momentum. In whichever one it loses, for whichever case the disk loses the least amount of momentum, the rod is going to gain that much momentum, the least amount also. And wherever the disk momentum changes the most, that's where the angular momentum of the rod is going to change the most. So for this one, when the disk bounces backward, it initially has velocity VO, but it has final velocity negative VO. So the overall momentum of the disk changed quite a bit because it had to stop and reverse directions, which means that it's going to transfer a lot of angular momentum to this rod. So that'll be the number 1 with the disk bouncing backward. For number 2, if the disk comes to rest, it had enough energy or enough in the collision to stop it, so all of that momentum was then transferred into the rod, so that's number 2. But if the disc sticks to the rod, then it's kind of keeps on going in that same direction, but starts curving off a little bit, so not as much momentum was lost in that case, which means less momentum was transferred to the rod. So the disc sticking to the rod is number 3. So now for part B, we're going to suppose that the disc does stick to the rod upon striking it, and we want to derive an expression for the angular speed of the rod after the collision has happened. So, because this is an isolated collision, the angular momentum is conserved. So I can start just by saying L initial is equal to L final. And this one is very similar to the one that we did in the notes because you have an object moving in a linear fashion that is sticking to an item that is rotating. So we're going to set this one up very similarly in that the initial angular momentum will just be the angular momentum of this object, which is the linear momentum that we have to put in angular form. So that is going to be, it's the formula mvr, which I'll just write that formula up here, mvr. So the disk has a mass of m over 3. It is moving with a velocity VO, and the r, the distance from where it strikes to where the pivot point is that distance x. So we have m over 3 VOx is equal to, now after this disk hits the rod and sticks to it, the rod with the disk are rotating as one item together. So because it's now a rotating object, we're going to use I omega. And ultimately, we're trying to find what the omega is, so we're going to divide both sides by I, but first, we actually have to come up with a formula for the I. So the I is equal to, now if you look on the formula sheet, or if you derive the formula, or do an online search, for a rod rotating around its left end, the rotational inertia is 1/3 ml squared, which in this case 1/3 m. The L is the length of the rod, which in this case is the D. So it'll be 1/3 md squared. That part is just for the rod, but we have to add on the rotational inertia of the disc, which is stuck to the rod. And whenever we have a single particle or a single object revolving around something, it's always mr squared for the inertia. Or in this case, the m is m over 3, and the r is that distance x from where the disk is hitting. So it's m over 3 times x squared, and then this second term, we can say, is just for the disk, but this whole formula for the rotational inertia, that's what we're going to have to substitute in for this I right there, and then solve for the omega from that. And you're going to end up with, for your final answer, you're going to end up with multiple fractions within fractions. So to clear things up a little bit, you probably should go through and multiply that whole entire fraction by a 3 over 3, because 3 over 3 is equal to 1, so it doesn't change anything. But by multiplying the numerator and denominator by 3, it'll get rid of the 3 in the denominator of this part, as well as both of these 3's in the denominator. In part C, we're going to suppose this time that the disk bounces backward with the same speed VO upon striking the rod. So when it's going toward the rod, it has a speed of VO, and when it bounces off it, it also has a speed VO. If we're looking at this in terms of velocity, that would be a negative VO because it's in the opposite direction. So is the magnitude of the angular impulse imparted on the disk by the rod greater than, less than, or equal to the magnitude of the angular impulse imparted on the rod by the disk? And once again, because this is an isolated collision, that means that the angular momentum is conserved. So that means the change in the total angular momentum, the delta L, will be equal to 0. So the gain in L, the angular momentum for one of the objects, will be equal to the loss in angular momentum for the other object, so that the overall total change in angular momentum is the same. And the change in angular momentum, that is the angular impulse. So we can say that the angular impulse for one object is equal to the angular impulse for the other object, since they both have a momentum change by the same amount. So you can put equal to for that one, and just discuss for the justification how the gain of one is equal to the loss of angular momentum for the other, since the total angular momentum was conserved. And in part D, derive an expression for the angular impulse that the disk imparts on the rod. Well, since we know that from part C, that they impart the same angular impulse on each other, we can just solve for the angular impulse imparted on either item. And it's actually easier to do for the angular impulse imparted on the disk, because the impulse is just equal to the change in the angular momentum, the delta L. And the change in the angular momentum is very easy to figure out, because it initially has, we're going to go back to using this formula up the top here, it has a mass of m over 3. For the v, the change in the velocity was 2 VO. It was 2 VO because if you take these two velocities, one positive, one negative, and subtract them, VO minus negative VO gives you a 2 VO. And then the R in that formula is just this X. So the final answer is, if I just clean this up a little bit, 2/3 m VO X.